Next talk is running away from the T-parameter solution to the W-mass anomaly by Gupta. Please start.
Hi. Thank you very much for this invitation. Today I'm going to talk about running away from the T-parameter solution to the W-mass anomaly. And so let me start. So this slide, I think, is, as all of you are very aware of the content of this slide, given the topic of this workshop. So the CDF collaboration has recently announced the most precise measurement of the W mass. And the reason for all the excitement is that the measurement turns out to be inconsistent with the standard model prediction that you can at 7 sigma level. So the prediction from the Electroweak fit, and here I'm quoting the PDG value, and it also disagrees with the global average of all the other measurements. So that is the reason for all the interest. Many BSM solutions have been proposed for this. Is my slide not moving? Just one second. I think the slide didn't move. Just one second. Yeah. So just one second. Go to full screen. I think my slide is not. Just one second. Okay, can you see my slides moving? Yeah.
But can you play?
Yeah, but if I do play, I think my slide is not moving. Okay, can you see it move now to the second slide?
Yes.
And okay, so now I'm in the third slide. Can you see it says EFT approach? Can you confirm that you can see the slide saying EFT approach?
Yeah. Yes, we see EFT approach. Yes.
Okay, thank you very much. So, yeah, sorry about that. So multiple BSM solutions have been proposed to address this anomaly. So assuming that the measurement is correct, so there is indeed, it means that there is an issue with standard model and we require some BSM explanation. So in many of these new papers that have come out, an EFT approach has been used. So if the new physics that is being proposed is let's say more than a TeV or something like that, a very frequently used methodology is to do a SMEFT fit. And when I say SMEFT fit or SMEFT fit, I include ST parameter fits, because as you know, for heavy new physics, the ST parameters can be connected to operators. So first we do a SMEFT fit. Let's say with some of these papers including only SNT parameters, maybe only universal new physics, and then you ask the question, what kind of new physics will give me this pattern or these values of SNT or these values of Wilson coefficients once it's integrated out. So this has been the approach followed in many papers where you do the fit and then try to get the right value of SNT. So for example, you might have, there have been various models. You can have Z prime, leptocoques, all kinds of models. You integrate it out and you generate these two operators written here. This OWB gives a contribution to the parameterizes basically the S parameter, and the OT when you go to the and the OT gives you the T parameter. So any new physics that gives you these two operators with the right Wilson coefficients should can be an explanation for this anomaly. So the first step is, if you just include these two operators, what kind of fit do you get? So I've given just one example here from one of the papers for a fit given these two parameters. And then once you know which region is allowed by the W-mass anomaly, you can ask the question, what kind of new physics models will get you to this region once you integrate out? So the main subject of my work, which I'm going to talk about, is what about running? So as you all know, there should be an intermediate step. You integrate out something at the high scale, and then you have to run down to the low scale. Or I mean, if you're doing it from the experimental point of view, you try to do a fit at the low scale and try to see what new physics at the heavy scale will give you something consistent with this fit, but you include running effects. So now you might think, and I think this is the logic that most of the papers, and it's not there's nothing wrong in this reasoning, that you might think that that running should be subdominant. After all, you have this loop factor, and you're not going to run for a very long time in energy scale. So it seems that this, because of this loop factor, including the log, it's a small thing. So it should be a subdominant effect. But the main point of my work was that all these. So let's say at a given scale, let's say at a given scale one, let's say at lambda equal to 1 TeV, all these Wilson coefficients are not constrained at the same level. So for example, the T parameter might be, you might get is the CT has to be, because it's a very precisely measured observable, all these electroweak observables. So maybe at 1 TeV, so this is just an example just to motivate what I'm doing. So let's say CT might be 0.01, and then but there can be another operator which is not as well constrained as the T parameter, which runs into the T parameter, and then even with the loop suppression, it can give you a contribution you cannot ignore. So that's the main point of this paper. So we want to identify operators that contribute to the running of CT and CWB, let's say, and then see which of these operators are not so well constrained, and if they can explain the W-mass anomaly. So in such a scenario, at the UV scale, you don't necessarily need the T parameter or the S parameter operators, the CT or CWB. You can have some other set of operators that are giving the CT and CWB at the low scale. So you need definitely CT and CWB at the scale MW, but not necessarily at the high scale. And this will completely change what you think of the UV completions, because it will be a different set of UV completions that will give you these operators. Okay, so next slide. Now, of course, if the Wilson coefficients were indeed of all of the same order, like let's say all the Wilson coefficients were of similar order, all of them were order 1 or order at some scale, you can at least parametrically ignore these terms, and this is the limit in which this is the limit that has been considered by most of the work so far, which do not consider running. So in this limit, where you will indeed explain the CT and CWB will arise from CT and CWB at the high scale lambda. So then of course you will go back to the set of UV completions we have been discussing, and the standard things that give you a T parameter like triplets and so on. But so the main argument in this work is that this is only a subset of all the solutions. So this is, of course, this is kind of so the parameter space I will derive, the SMEFT parameter space that is consistent with the anomaly at the matching scale, at the scale lambda, will be larger than this parameter space. Of course, it will include this special case where where you can neglect the running effects. But if you include the running effects, you get a larger set of possibilities that are consistent with the anomaly. So that's why I say the solutions considered so far are a subset of the other possible solutions. all
we
the
have
possible
question.
solutions. Yeah, please.
Yeah, hi. Can you go back to the previous slide, please?
Yes.
Okay, so if I understood it correctly, your idea is to use operator mixing effect. So like when you integrate
Yeah.
the heavy state, you might not necessarily generating like large enough CT, but other operators which has mixing with the T operator eventually along the RG trajectory can
Right.
induce a largish
Right.
effect in the IR, right? However,
Exactly.
naively, I'm confused because the T operator requires extra custodial symmetry breaking. But then that means that the other operator, which mixes with mixes with the T operator, also has some sort of a custodial symmetry breaking effect in it. So then the question could be that
Right.
what kind of UV physics, which does have extra custodial symmetry breaking, generating other effect, other operators, not generating T operator. Are you thinking of some sort of fine tuning somewhat happening so that CT has
So,
not been
so I,
generated?
so I am quite agnostic about the UV completion as right now, but I think there are, I mean, there are instances where, I mean, yeah, this is a, so you're right. I mean, if you want to run into CT, you also have to break custodial symmetry, and then your question is that whether this new physics, so that's a separate. So for me, I'm just looking at the level of EFT. So I'm not thinking about UV completion so much, but like. Yeah, that's a good question, but I mean, I have to think how, but I think there are like there. So it's not that I'm saying CT is zero. So I think that's the answer. So it's just that there can be CT and other things, but it will change the parameter space. So I mean, you can have a situation where there is CT, and as you will see in my final plot. So I think, yeah, I think the answer to your question is that that it's not that so I mean, in my set of EFT solutions, it is true that I will show you solutions where CT can be zero, but more generally, the space of all solutions will include places where CT and this new operator are of the same order, but not what you think if you would just do a fit at the IR. And I'm saying that because I looked at a bit at like you maybe composite. I didn't think too much, but I think it can be possible to have new physics scenarios where you can I mean but I guess you're right that in those scenarios you will have both CT and these operators at some yeah yeah. So I mean, if you will see, when I'll show you a final plot, you'll see there are regions where you have negative T. So for example, you can have negative T, which is not compatible with the anomaly, but it can be made compatible if you include running effects. So for example, that will be an example where you have both CT and these new contributions. Yeah.
Okay, thanks.
Okay. Yeah, so we will, I think in the final slide, I'll again come back to this question and I'll show you regions. Maybe you are right. Although I'm not entirely sure, maybe you're right that just asking for CT equal to 0 is maybe and other custodial breaking effects may be fine tuned from a UV perspective, but I'm not sure of that. But I will, but most of the region will have a non-zero CT, and it will just be a different region than the region you derive just from the IR, if you don't consider mixing effects. Okay, so
Right.
yeah, so the upshot will be that, sorry? Yeah.
No, what you said last, that makes more sense because the T parameter has both positive and negative contribution usually. So you might start with a negative T, but like you might turn that sign into the positive into using the
Exactly. Yeah.
renormalisation
So
group effect.
yeah,
That may be possible.
exactly. So what I would the good way to put is that we don't require like this thing that you have to have a positive T. It's not like if you include running effects, you can have negative T, and then that scenario is not doesn't contradict like doesn't require tuning according to your reasoning, I guess.
Right. Okay, good.
Okay.
Thanks.
So yeah. So okay. So yeah, although I mean I've really not thought of UV completions too much, but I think I did think enough to think that there should be some UV completions for the new regions I am proposing, but for this talk let's stick to the EFT. Okay, so what we'll show is that at a few TV, you will generate all these other operators. I will of course go through what these operators, what these my notation and so on, and then the running of these operators will induce OWB and OT. Of course, as a special case, we will include the solution where the dominant contribution comes from the UV value of OWB and OT. But we'll find a much larger parameter space consistent with the CDF anomaly at the matching scale. Okay, so so I mean, as I will argue in the end, this observation is completely valid in the most general case, but we will focus on universal new physics just because it's more manageable. But I mean, because if you do non-universal, you might have to consider in the most general case, maybe, I don't know, 30 operators or something that give contribution to MW via running effects. But universal new physics is more manageable, and I'll argue in the end that these arguments should hold even more probably for the general case where you have all kinds of operators. So if you want to stick to universal new physics, there are these 16 operators that can completely parameterize universal theories. So all these operators are bosonic, so they affect the bosonic sector. And this is so let's try to do the most general analysis on find which of these operators can run into OT and OWB, which is the S parameter. So this anomalous dimension table is taken from one of my previous papers, where actually we did make this point that different operators are constrained at different levels. So it's it's important that like a weakly constrained operator can run into a very strongly constrained operator, and these effects can become important because then the running, despite the loop factor, can become is something important. So so 6 operators contribute to the running of OT of these 16, and 10 operators contribute to the running of OWB. Okay, so now we want to see which of these operators are constrained at what level, right? So the first set of so the constraints will come from electroweak precision observables, from diboson physics, so like triple gauge couplings and so on, and finally from Higgs physics. So to start with, we start with electroweak precision observables, and so the S and T parameter were of course proposed for the first time by Peskin and Takeuchi, but later it was generalized by Barbieri et al. To include these 2 other parameters, which are called the W and Y parameters. These are like terms with 4 derivatives. And so this recent paper by Strumi after the anomaly, actually, so the reason I took the fit results from his paper is because he actually marginalizes over W and Y. So when you look at this SNT fit, it's not just it is marginalizing over W and Y, and the W and Y actually are very well constrained now. Even so, LHC data like PP to LL and things like that can because like as you can see, this W and Y operators, like if you use the equation of motion, it can become like it can give a contribution to like 2 fermion. So it can be like you can write it as a sum of operators, and one of them can be like a current operator. So you can have a 4 fermion operator which can be very well constrained at LHC, for example, PP to LL or something like that. And so these recent W and Y constraints, actually also reported in the Strumia paper, are coming from LHC. So the LHC now constrains these 2 parameters gives you the largest constraint on these parameters, the strongest constraints on these parameters. Okay, so once you marginalize over W and Y and assume that the new CDF measurement of MW is correct, you get this fit shown in green on the right-hand side. So these are the constraints. Important to see is that everything here, all these 4 parameters, S, T, W, and Y, are constrained very well. So these are the most precisely constrained observables in the electroweak sector. They're per mil level or less, so 0.001 or less. So everything, yeah. So the next set of operators can be constrained. So I'm just going through the 3 sets of constraints, and then I will identify which operators are poorly constrained and also run into S and T. So the next set of constraints will come from diboson data. So from modification of WWZ and WW gamma vertices, which was first parameterized by in this paper by this Hagiwara et al. Paper. So these contributions can give you deviations in diboson WW production at LEP or WZ and WW production at LHC. So now already, because LHC can go to much higher energies, if you see on the right-hand side, I show the LEP bound. And I also show various bounds from Atlas and CMS paper, but there's also a paper by theorists, by Grosjean et al., who looked at it very carefully. And this yellow region is the present bound. So if you, you can, as you can see now, we have surpassed the LEP bounds because we go to much higher energies, and you can use the fact that these processes grow with energy to get very strong constraints. And so these triple gauge, so this yellow region is the constraints on this triple gauge coupling. And now you can translate this constraint to the Wilson coefficients, because these operators OWB, OHW, OHB, and O3W contribute to this. Of course, OWB is also the main contributor to S parameter, so it's already constrained. But then you can get some constraint on the other three operators as well. So these, if you look at this figure, are constrained at a few percent level, not so the constraint is in 1 to 2 order of magnitudes less strong than the constraint on the like S and T parameter of the W and Y. Finally, for the Higgs part, I mean, this is not important. It's just that like the initial table I showed the Higgs operator written in a given particular basis. I am just rewriting 2 of these Higgs operators in a way which is convenient, because one of these rewritten operators, OH minus, is what contributes to the running of SNT, and it is also the one constrained by experimental data. So that's just a change in notation, but I mean, I don't expect you to remember the names of the operators anyway. But just for the sake of completeness, so now with finally are constraints from Higgs physics. So these operators can cause deviations in the HVV vertex, so the HWW and HZZ vertex. And here I've included things like H2 fermion, although the universal operators won't contribute to HFF. They can in a universal way, but I've included many. I've included everything because in any case, when you are doing the fit, you need to you need to include everything, right? You can because everything enters the fit, the Higgs fermion couplings, everything. The final constraints I will get on these universal operators, and I get something. So from the Atlas collaboration, the latest result is given on the right-hand side. And now you see that these are order 1 constraints, okay? So I've normalized things in a way that you can really compare across this, okay? So the precision, electroweak precision constrains things at per mil level, or even less, or 10 to the minus 4 to 10 to the minus 3. Then the TGCs are a few percent, so 1% to 10% level, so 2 orders of magnitude less, and this is at order 1 level. So this is from the Higgs fit, from the Higgs couplings. Okay, so now we want to see so some of the operators are too well constrained and their RG contribution can indeed be ignored by using the usual logic that is loop suppressed. So for example, you can have contribution from this O2B and O2W. This is what gives you this Barbieri W and Y. And so if you write down the contribution to the T parameter from the RG contribution, and you can estimate it, it is really small. It is much smaller than even the precision with which you measure T parameter. So you can really ignore it. So you can ignore many of these operators. For example, the operators written here, OBB, OWW, O2B, O2W. And also we can ignore O3W, because although it is a bigger contribution, it's still something that can be ignored. So this leaves us. So the main point is that this leaves us with 3 operators basically. So we are left with 3 operators that are quite poorly constrained. So you have these 2 operators that are constrained at the few percent, so 1% to 10% level by diboson measure. So these are the operators that give you anomalous triple gauge couplings. And then you have this operator in the Higgs sector that is constrained by the HVV vertex, so H2WW, H2ZZ, and this is an order 1, so it's like 10% level constraint. Okay, so we will look at the running effects due to these 3 operators. So first, what is the RG contribution due to OH minus, so this Higgs physics operator. So this is the operator that gives you a deviation in the HVV, the HWW and ZZ vertex. And this has been considered in other papers, actually, not in this, maybe not in this EFT language, but it is well known that if you shift the HVV vertex, then it can give you contribution to the SNT parameter. So it's not often not written like this. It's written as you shift this kappa V that I introduced in the previous slide. So maybe I'll go back. So this kappa V, the first term on this first box, is the deviation of the coupling HWW and HZZ. So once you have a non-zero kappa V, you do generate an SNT through loops because which is logarithmically divergent. But you can, but in the EFT interpretation is really, so also here, I should say that, there's a mistake in the notation. So the CH here is actually CH minus, okay, in this big box. So this effect in the EFT language, you can think of as the contribution of this operator OH minus, which is giving you this deviation in kappa V to the running of SNT. So this was considered, but the problem is that, like, in a large class of UV models, so if you do the fit and everything, it's not hard to see. So if you see here, to get a positive delta T, you would need a negative CH minus, and turns out that you need something in this range, something under minus 2.5 to minus 1.4 to fit the CDF measurement. And this is indeed a very simple, nice solution. But unfortunately, I mean, if you in a large class of UV models, you can show that the CH minus has to be bigger than, it has to be positive or non-negative, more than equal to 0, because of various reasons that are, so there are exceptions. For example, if you have scalar triplets, I think the only exception is if you have scalar triplets, you can have a negative CH minus. But otherwise, on general grounds, within SMEFT, you can show that this operator should have a positive Wilson coefficient. So from arguments like unitarity, analyticity, and like they also consider various special cases. So they make this argument in this paper, Ratazzi, Low, and Vicky, that apart from some exceptions like scalar triplets, as I said, this is positive. So this is unfortunately cannot. So this paper that I mentioned here, this Cacciapaglia and Sanino paper, they actually don't look at it in the SMEFT framework. They are looking at it in some kind of like non-linearly realized parameterization, and then indeed it may be possible to have a negative to explain this thing. But if within the SMEFT, if you have this operator, this is problematic. So going to the other two operators now, the other two operators that give contribution. So this is the OHB and OHW that give contribution to the TGCs. Now the question we want to ask is it possible? So here I show you 6 different plots, assuming so we have to now assume what is the UV value for the SNT. So you start with some UV value, so the CWB and CT at lambda, at the scale lambda. And you see that for the UV value, I've taken 6 different possible UV values. So on the top left, I take that the T parameter is 0 at the UV scale and the S parameter is negative. Then I take the S parameter, so different values of S parameter as we move along the first row. And similarly, in the bottom row, I take a positive T parameter, but half of what you kind of require. So just to show that you can just now vary the T parameter, doesn't have to, so the values of T parameters that I've chosen are, if you just look naively from the fits we are doing, you would not, and in the next slide, you will see even negative T parameters. So I somehow, so here you don't see them. So depending on the value of S and T, I can try to plot what is the region consistent with the CDF MW, that's shown in green. And then this region and the axis here are the 2 operators that give you the TGC. So I'm showing you in the plane of these 2 operators that give you the TGC bound. I'm assuming some UV value for the operators that give S and T. And then I'm trying to see if what are the bounds on these operators from this diboson is given in yellow, and then what is the region where along with this UV contribution of T and S, I can give I can explain the anomaly. So I am looking for the overlaps. I'm looking for the overlap of the allowed region from the TGC bounds and the region that is consistent with the CDF anomaly. And I get this kind of orange region. And the interesting thing to see is, of course, that even with T parameter equal to 0 or a much smaller T parameter than expected, you can explain the anomaly quite well. Also, it's interesting that this dot, if you see this dotted line on this yellow, the TGC bounds, that is the future projection, also from this Grosjean et al. Paper I should have mentioned. So these are the future HLLHC 3 inverse autobahn predictions. And you see that some of this region, which is right now allowed by TGC bounds, most of this region will be ruled out. So most anything outside the dotted line, you will be able. So if the MW anomaly is indeed correct, you should see, and if some of these solutions are correct, then you can see you can see these effects also in diboson production, and that is interesting. The other thing is, of course, that we are looking at a much smaller scale here. So something like lambda equal to 800 GeV instead of, like, if you want to explain everything from a UV value for the SNT parameters, that would be a few TeVs at least, because it's a tree-level contribution. On the other hand, like, because this is now one loop suppressed and you need larger Wilson coefficients, so you need a lower scale, you need a bigger effect, because now the running is one loop suppressed. So that's why even for direct searches, whatever new physics is generating, this is much lighter. So maybe not exactly 800 GeV, but something around a TeV. So if these RG, if these new regions of the parameter space uncovered by RG are correct, then indeed are giving rise to the MW anomaly, then there is more hope for future measurements that can confirm it, both indirect measurements like diboson measurements, or directly looking at the new physics generating these operators. So now coming to this plot, which probably is the most comprehensive one. So here I look at what value, UV value of S and T I need to given these two operators. So the earlier plot was in the plane of CHB and CHW. Now I'm making a plot in the ST plane, but these are the matching scale values of S and T. Okay, so this is this is basically so if you have no running at all, then this is also the value you'll have at the IR scale. But now I marginalize over these two operators that can give big running contributions, so over CHB and CHW. And now I see that so if you look at them, so there are three ellipses shown. If I look at the middle ellipse, the CHB equal to 0, CHW equal to 0, that is very close to the ellipse from the Strumia paper or the other papers that do this ST fit. Of course, it is still a bit different because there's some self-renormalization, right? There's some self-renormalization of the SNT. The operators self-renormalize a bit, but that is, of course, a subdominant effect because that is one loop suppressed compared to the UV value. But still, it is not a completely negligible effect. But otherwise, it's more or less in the region you expect, positive T parameter, so the middle ellipse. But now, once I change the value of CHB and CHW, I can cover a much bigger region. So in particular, you see this green region now includes negative T parameter regions. So as I was saying to the answer to the question that was asked, so the point of this paper is not that, although this is like one of the interesting things to show that you can have at the EFT level, that you can have a 0 T parameter at the matching scale and still explain the anomaly. But the more important point to make is that you can have a much larger range in the ST plane that gives you that is consistent with the anomaly at the matching scale once you consider the effect of these other operators that can run into it. So basically what is happening is that once you have the CHB and CHW, you are, because it gives some contribution to SNT itself, it is shifting the ellipse, right? So it's shifting the ellipse from the 0. So because it's giving some contribution to SNT, it's like like if you subtract that contribution, you're shifting the ellipse, and now that is the region you want to go to. So it's quite so like people would have seen similar plots for like sometimes you see that, like, yeah, so in the presence of some new physics or some you can shift the SNT. So that is basically what is happening. So that's why because this and the shift so it's shifting kind of the origin of the SNT ellipse, and the shift is substantial if you take these values. It is and the shift is substantial even while CHB and CHW are within the TGC constraints. So all these values are within the TGC constraints. We marginalize taking into account that CHB and CHW should be within the TGC. Now that was the main result of the paper, but I just want to say that this is, although I did it in the context of universal operators, this is only for practical reasons. So if you want to generalize to the non-universal case, so the 16 bosonic operators, you can keep these bosonic operators, but you have to add another 43 operators to get a full 59 dimensional basis for a single generation of fermions. If it's if you have like more, if you want to include all generations and include flavor indices, it's much more, of course, but this is just to give an example of the number. Now, instead of just this OWB and OT, there are 4 operators actually, as many of the other papers that will be discussed even today in this workshop will do the more general analysis. So there are 4 operators that give tree-level contribution to the W-mass, and many more operators that will contribute to these 4 operators via RGFX. So now, in the most general analysis, you should include all these operators, and including all these operators might result in discovery of many new allowed regions at the matching scale. Just like we found this region in the UV where you have this SNT. Just one second, there's something in the chat I should. Okay, so yeah, I'm almost done. So just for 1 second. Let me go back to play. Yeah. So this is really the slide before the conclusion slide. So now including these operators will result in the discovery of many new allowed regions, and the regions shown in the but the regions that we found, that's shown in the CWB, CHW, CHB plane, the TGC operator plane, will remain because you can go to the limit where these new Wilson coefficients, these 43 new operators are all 0. So in that limit, of course, these solutions remain. Now, even if they're not 0, if you include their effect, if anything, it will, and if you marginalize over them, it will only make this region bigger. So if I look at the region in the universal parameter space that explains the anomaly, and I marginalize over everything else that is coming from non-universal, I would only get a bigger region. And so it's just a more complicated problem practically, but it is completely conceptually. This is not something limited to universal new physics. I don't want to give that impression. So sorry. So that said, so that brings me to the end of this of my talk, and I will leave the conclusion slide here. So the main point, of course, was that because different operators are constrained at different levels, renormalization group effects, sorry, I said renormalization gauge effects here, can be crucial in determining the SMEFT parameter space that is consistent with the anomaly at the matching scale. And we illustrate that in the context of universal operators, and it show that it is possible to have a vanishing or even negative T parameter at the matching scale. And for as far as one loop contributions, and finally, because these new regions, because I have a much bigger parameter space that is now consistent with the anomaly, you have regions where the new physics scale can be very low, around 800 GeV, and this enhances the possibility of probing new physics, both in direct and indirect searches in the recent future. Okay, thank you very much.
Okay, so we have a question.
Yeah, thanks for the very nice talk. I have
Yes.
one basic question. So
Right.
say I have some UV physics, and then if I integrate out the UV physics at tree level, I happen to generate, smallish or T parameter with some other largish operator, which mixes with T operator, therefore generating large effect in DIR. And I'm just wondering, what if I integrate the UV physics at one loop level? Then that one loop level in principle should take care of a little bit of a operator mixing effect. So then say at two loop level, I wonder whether it actually generates a largest T operator. And then if I use that, whether it more or less captures.
Yeah. Right. So no, I'm not sure. integrating at one loop is not including the running, right? So integrating at one loop is still like you're looking at energy scales above the cutoff, and you're now including one loop diagrams. But the running is momentum scales between the cutoff and MW. So when you integrate out, you are only you're integrating out physics which is at scales higher than the cutoff, and the running is something between the cutoff and MW. So I'm not, but having said that, I think it is still interesting to look at this, because as you're saying, I'm talking about operators at different levels of. So some operator is Wilson coefficient is large, some Wilson coefficient is small, and this is something interesting to look at. However, how I see it, so another way to see it is that it's not necessary that all these operators are generated at the same scale. So maybe the T parameter is generated at 5 TeV and it's much smaller, and something else is generated at 1 TeV. So you can also have scales. So that can give you this kind of hierarchy in, or it can just be that one is much smaller, as you're saying. I don't know if this is some kind of tuning, but yeah, one Wilson coefficient can be, I guess, much smaller than the other. Maybe it's one loop suppressed or something, or the other thing can be that the operators are generated at different scale. But you are right that it is interesting. Like if you have to think of UV completion, it might be important to think in loop effects while integrating out because of these kind of things, because these operators are constrained at different levels. So definitely, for example, it won't be enough to show there's no T parameter at tree level generated, because even a smallish T parameter can have a big effect, as you're saying. So it will be important to look at, okay, is it generated at one loop? I mean, so you have to go to the order which is so if a smallish T parameter can explain the CDF anomaly as is, so let's say I'm integrating out at 1 TeV, then you have to go to the required number of loops. That's correct. Yeah. Mm-hmm.
Right. Okay. Anyway, so even though the level of integrating out versus RG effect, even though conceptually it is somewhat factorized feature, but there is a little bit of entanglement there too, right? That's why I was invoking. In other words,
I see.
of mixing the operator can be also viewed as have the one higher loop diagrams effectively generating small other operator like D parameter in this game. So I was wondering whether one can understand better the exact level where how much they're entangled or how much we can factorize these two. Anyway, so that was great. Thanks a lot.
Right. No, that's a good point. But of course, in the end, it is what I'm saying. The effects I'm saying is indeed a one loop diagram. So if it's a TGC diagram contributing to MW with a vertex with a vertex of 3 gauge boson. So it is indeed a loop diagram, as you're saying. Yeah, as you're saying, the question of whether it's coming from the IR, like whether yeah, exactly. So there, yeah, I mean the basic way to see it is, of course, that like when you go to energy scales higher than the cutoff, you're kind of looking at integrating it out, and then this. But as you're saying, there are subtle effects that it's not easy to factorize always these things, especially because my scale is not so high, it's 800 GB. But yeah, it's a point well taken that, yeah, like if I have to go to UV completions, we should take into account all these effects. Yeah. Right.
Okay, so I think that we are really behind the schedule. So let's thanks to speaker again.
Okay, thank you very much for inviting me. Yeah.
Okay, thank you.